Good evening and welcome everybody. Thank you for coming. My name is Mark Ledbury. I'm the director of the Power Institute and I teach here at the Art History Department here at UCID. And I'd like to thank you all for coming. And first, let me begin and acknowledge that we're on Gadigal land, unceded land, custodianship over which has for long been held by the elders past and present of the Gadigal people of the Eora Nation. And as we remember and respect the thousands of years of teaching and cultural transmission on this site, let me also pay my respects to any First Nations people in our audience tonight. I'm delighted to be convening this panel, which is called The Machine Eye, as you can see, which is part of a series of panels and talks, which some of you, I think, have been attending regularly, called Photography Falls Apart, convened in association with our wonderful colleagues at the Chau Chak Wing Museum, with the discipline of art history and the photography cultures group, research group here at the University of Sydney. And it's inspired by actually two exhibitions downstairs, but particularly photography and the performative, the exhibition curated by Katrina Liberio, who is here tonight. And it's on level 1. And if you haven't seen it or the staged photograph, another wonderful exhibition that is on here, I recommend you do so. Today, we're exploring the theme of the machine eye, which, of course, you could argue the camera has always been, but in particular, we're looking at how human vision has been enhanced, extended, challenged, in fact, and interfered with, you could almost say, by new technologies and the worlds that these new technologies are opening up, or do open up, from the nanoscale to the mind-bogglingly big, via the thorny human scale issues of machine learning, AI, and its associated dilemmas. We're exploring today big questions then of vision and seeing, of what it is and how we do it. And this interdisciplinary exploration is part of what we at Power are calling the Visual Understanding Initiative, which some of you will have heard of, where we're trying to ask the questions around the university with our colleagues across disciplines. What is it to understand the world visually? How do we do it? What are the conditions under which we see now? How are we to deal with the new imagescape of the 21st century with all of its many promises and threats? Today's panel owes a lot, I have to say, to the organizing genius of Power's program supremo, Nicholas Croggan, and I'm grateful to Nick, and also to many other colleagues, especially to Katrina Liberio and to Donna Brett, and all those at the Chau Chak Wing who have made this event and this series possible. So it's my great pleasure to introduce a wonderful lineup of speakers, and I'll try not to talk too much and let you get on to it. But what I'm going to do is I'm going to introduce all three of them now, and then they will speak one after another for around 10 minutes. And then we're all going to gather on those chairs so that you can ask us questions and we can our panelists can attempt to answer them. So our first speaker in the order that they'll be speaking is Professor Julie Cairney. And Julie is Pro-Vice Chancellor Research Enterprise here at the University of Sydney, where in that role, she supports strategies which enhance our collaboration with industry, improve research commercialization, etc. But she's actually a professor of materials engineering, and she's been a leading researcher specializing in using advanced microscopy to study the three-dimensional structure of many materials at the atomic scale. So we are talking very small. From 2016 to 22, she was the CEO of Microscopy Australia, which is a national infrastructure that provides open access microscopy and expertise across Australia. And our following Julie will be Eleanor Zeichner, and Eleanor is the assistant curator of the UTS Gallery, curator of the very recently closed exhibition Image Interrupted. I don't know if any of you managed to see it. It closed last week. It's fantastic, which really did bring a focus on artists and their interaction with the threats, promises, and complications of AI and the generated image in various forms. Other projects, curatorial projects, include Forensic Architecture Cloud Studies from 2020 and After Technology. She's written for many publications, including Unmagazine, ArtLink, Art Australia, and Volt. And she's also been an editor of the Runway Australian Experimental Art. And our third speaker will be Professor Peter Tuthill, and Peter is as many of you will know, an expert in astrophysical imaging, studying stars and their immediate environments at the new, technically possible, unprecedented resolutions. After obtaining his undergraduate degrees at the University of Queensland and ANU, Peter moved to Cambridge, where he graduated with his PhD, and then took 5 years, went 5 years as a postdoc research astronomer at the University of California at Berkeley, in a research group led by the Nobel laureate Professor Charles Townes, and then returned to Australia in 2000 and has held a number of Australian Research Council fellowships up to his present appointment as a future fellow. And Peter works at the Sydney Institute for Astronomy, which is one of the largest astrophysics groups in the country, of which I think he was director until recently. Is that correct? Yeah, that's right. So thank you. Please welcome all our panelists, and I will hand over now to you.
All right. Well, thank you for that lovely introduction. As Mark said, my name's Julie Cairney. I'm a professor in the Faculty of Engineering here at the University of Sydney. And my expertise is in using advanced microscopes. My specific expertise is around the atomic scale microscopes, so the highest resolution microscopes. But most of my research is very much industrially focused. So I actually do work with industry trying to solve real world problems related to whether steel can carry hydrogen, whether we can develop new photovoltaics by providing my partners with the atomic scale information that they need to solve those problems. And until recently, I was the CEO of an organisation called Microscopy Australia, which is a network of big central microscope labs that are shared across the country. And I was the director of our central microscopy facility here at the university. And I was lucky enough to be overseeing some of the work that produces these just incredibly beautiful images that come out of our instruments at a scale, of course, that you can't see with your eyes. So I want to just kick this off with these images. These are all images of beach sand. And if you were to take the sand from Bondi Beach and put it under well, this is just really a magnifying glass, you would see that the grains of quartz that make up the sand at Bondi Beach look like little tumbled rocks that have been evolved in the ocean from the sandstone in our environment. But if you took the sand from the beach at Magnetic Island and had a look at it under a magnifying glass or a basic light microscope, you would see that the sand on Magnetic Island, although the beach looks very similar and the sand looks very similar if you hold it in your hands, it's actually made up of these incredible little coral structures, because the sand on Magnetic Island is made up of the coral that's come off the reef and turned into the residue. And so the things that you see with your eyes aren't necessarily what they comprise. And which of course is why it's so important for us to be able to understand things at length scales that we can't see with our eyes. And so I'm going to take you on a little journey across some different length scales with some different microscopes. And we're starting with sand, which is kind of on the limit of the resolution of what you could actually see. And work my way through the increasingly powerful instrumentation and what we can do with it. So I want to start with this image of Anthony Leeuwenhoek. He was a lens maker in Amsterdam in the 1600s, and he produced the world's first microscope with his, lenses for spectacles. This was, and he put them in a sort of configuration that allowed him to actually look at something at a microscopic length scale. And he looked at all sorts of liquids and solutions, and he found in them that there were just all these incredible little molecules or organisms all just moving around. And this was an absolutely revolutionary discovery that, in fact, biology is governed by microbiology, and all of these little organisms are affecting everything, and led to all sorts of modern medical knowledge. And this was enabled, of course, by simply having access to an instrument that allowed him to see that. And he drew these lovely images. This is an image of sperm. He even saw things that weren't really there. He saw these little dudes inside the sperm all curled up, and published these wonderful papers. And it was very clear really cute the way he's made it very clear that it was not through sinfully defiling himself, but instead this was residue after conjugal coitus. So now I want to mention that the sort of thing that Van Leeuwenhoek could see, and even with the best advanced light microscopes, the wavelength of light is actually between about, this doesn't work, 100 nanometers and 400 nanometers. So we can see maybe cells, maybe bacteria, but it's not possible to see proteins, DNA, any of these structures, and it's really important if we're able to design new technologies or understand medical breakthroughs or make medical breakthroughs, we need to be able to access that type of information. So this is an image of the first electron microscope. So to see things at a higher resolution than light will allow, scientists in the 1930s developed the first microscope based on electrons. So it uses the electrons that travel through our wires into our homes for electricity. It goes through a big vacuum, and this is the first electron microscope designed by Ernst Ruska in 1933. And I don't want to try to go into details of microscopy technologies, but obviously since that time, there's been just an absolute myriad of different advanced microscopy technologies that allow us to be able to access information at all sorts of different length scales. And again, these are just some of the beautiful images that we're able to produce using those different technologies. Now, if you look at these images, they look like art, right? They're really gorgeous. We've even had art exhibitions where we had an exhibition called Inner Space with Microscopy Australia that had stories attached to each of these images and the story behind them, and it travelled around Australia and went to a few great museums around the world. But over the years, there were a lot of people who would look at these images and say that they look a little bit like Australian Indigenous art, actually. And we always thought that was kind of a cute idea. And then Jenny Whiting, who's in the room here, actually started to talk to some Indigenous artists about whether this resonated with them as well. And what we learned was that it did. And what we also learned was that part of the reason that these look like Indigenous art is because when we look at these microscope images, we're looking down through a microscope at a surface, at an inner landscape or an inner space. And Indigenous art is also portrayed from that top-down perspective with this iconography that represents landscapes. And Jenny worked then with some really fabulous Australian Indigenous artists to create this exhibition we had called Stories and Structures. And the artists produced work that was inspired by or based on a microscope image. And these are just three examples. The one in the middle is a painting by Bronwyn Bancroft, and it's based on, in this case, an invasive cell that gets into marine organisms and actually is quite damaging. And she heard the story associated with that is similar to and represents colonization. This is a story. This one is called The Big Wet. It's a beautiful painting, really quite large in real life, based on a couple of microscope images, one of which is this one, which is, again, sperm, a bit of a theme here. And this is representing the cycle of fertility in especially the wet season. And this one was if I can remember rightly, this is quartz, and that's actually a very high resolution image where you can see the atoms. And these represent the sand hills that are made up of the quartz that you would find in Central Australia. And there's a dreaming story associated with the sandhills that resonated with that artist. So now that's a little bit about this kind of length scale. I'll just take a moment to maybe indulge myself and tell you a little bit about my own research. I work with a microscopy technique called atom probe tomography. And the best way to understand it is to actually see the data that comes off it. So this video here is an image of a needle-shaped sample. So we make whatever it is we want to study into a needle. In this case, it's an oxide layer because I'm studying corrosion because I'm a boring engineer. what we can do is reconstruct these maps that show us exactly where all the atoms are positioned within that needle, which we can use to understand the sample that we're studying, in this case, corrosion. And in this image, you can see iron atoms. You can see carbon atoms that are beautifully decorating the boundaries between the little crystals in this oxide. And you can see the oxygen that makes up the oxide. And that's really very valuable three-dimensional information for scientists who are studying corrosion. So how do we get that data? We take our sample and we make it into a sharp needle. We can do that with like an acid or something, or we can use an ion beam. And then, without getting too technical, we put an electric field on the end, and the atoms fly off and they hit something which is a position-sensitive single atom detector. So the atoms fly off, they hit that detector, and we can use the position that the atom hits the detector to back calculate where did it come from on the tip. And we can use how long it takes, which is related to how heavy the atom is, to work out what kind of atom it is. And then we can build up, one by one, a three-dimensional map that shows us exactly where those atoms are. And I am finishing now. So we can see, and what I use that for is a whole bunch of different industrial things. I just thought I'd pick one really quick example, working with minerals. I'm actually working with some geologists who study meteorites. So they have these cameras positioned around the centre of Australia, all pointed up at the sky. And when a meteorite lands, they triangulate where it landed. They go out on these field trips. They actually collect the meteorite, and then they're giving it to us, and we're having a look at the tiny little particles in the meteorite. They can work out which part of the solar system it came from the angle that it came in at. And so we're then able to do things where we can work out the age of the little particles in the meteorite, so they can work out the order in which the planets formed and do all this incredibly planetary science. And I wanted to show you that because I think that that connects how we can look at things at the atomic scale, and we can determine things about things that are happening on the scale of our solar system.
Thank you so much, Julie. That was amazing and very beautiful. I was very moved by that, actually. And thank you to Mark and Nick as well for having us, and to Peter, who will speak after. I'd also like to acknowledge that we're meeting today on the lands of the Gadigal people of the Eora Nation, and pay respects to elders past and present, and acknowledge that sovereignty was never ceded. I'm going to do, click. Oh, yeah. Oh, there's one more. That's me. All right. I'm Eleanor. I'm assistant curator at UTS Gallery, and I'm going to speak today on a few recent projects of ours that think about the machine eye as it relates to the work of artists, and how through art practice we might find new ways of thinking about image technologies themselves. And I hope you'll find that it's my contention that artists have always used new technologies in ways outside the commercial or industrial intention of those technologies, that they use the materials to hand and the technologies of the moment to depict and distort our experiences of the visual world, and to create new realities that blur the lines between fact and fiction. But I wanted to first share a couple of projects that we've recently presented before I talk about this recent exhibition, Image Interrupted, such as a project from last year called Objects Testify by artist Joel Sherwood-Spring, whose work you can also see in this year's Biennale of Sydney at White Bay Power Station and at UNSW Galleries. And this was a project, an extraordinary video work really, that examined the social and environmental ethics of technology in constructing and storing and sharing images, particularly in museum archives and surveillance databases. So what are sort of the ethics of us storing these materials? And considered the problems that arise when new technologies provide open access to cultural belongings and documentation of Indigenous people. This was a project from 2022 by Sydney McMahon, who was one of our inaugural UTS artists in residence, and worked with researchers in computer science at the Botany Tech Lab to develop this immersive video installation titled Maggot, which used brain sensing wearable technology to read the user's visual cortex and translate neural activity into real-time digital commands. So in this image, Sydney, the artist, is demonstrating the use of this technology, which sits on the back of your head, and you use it to provide prompts without, just with the movement of your eye. So it was presented as a kind of narrative, choose your own adventure, 3-channel video, and examined the act of looking, being looked at and being seen, and the relationship between our visual reality and our cognitive understanding. Yeah, so you sort of selected a narrative pathway for this, the main character, who is a maggot. And a little further back, this is a exhibition titled Cloud Studies in 2020 with UK-based research agency Forensic Architecture, which is their first solo show in Australia. Forensic Architecture is an incredible sort of interdisciplinary research agency, you know, initially composed mostly of architects, but they also include journalists, sound engineers, lawyers, all sorts of interesting people, founded by a architectural researcher called A.L. Weitzman. And this project brought together about a dozen investigations centered on the theme of toxic clouds, which is a very fitting theme for 2020, that year of bushfire, pandemic, and protest. Forensic architecture's use of architectural methodologies, and they combine that with sort of forensic image analysis to test the limits of visual proof. So looking at the scale of, you know, a pixel in an image, for example. So this, you know, this work, Cloud Studies, included examples of investigations such as this one, which was called the bombing of Rafah, in which they collected hundreds of images and videos uploaded to social media by people in Gaza in order to methodically compare the shape of smoke plumes in relation to the built environment. So where were they in relation to known architectural structures in Rafah? And that allowed them to create a 3D model of the event and then locate the exact munitions that were used in this attack, which was later used by Amnesty International to identify this as a war crime. And they're doing amazing work at the moment in, you know, the recent conflict in Gaza also. So I'm going to talk a little bit now about a current/recent project. So this show just closed last week, Image Interrupted. And in this show, I was thinking about how artists explore and expand on the materiality of machine-made images. So the humanness of texture and touch, of feelings and desire, how they might interrupt, how they might create new worlds and realities, and how they excavate the human from the machine. And perhaps suggested by these previous projects that I've just showed you, my feeling is that, you know, the acceleration of image technologies presents both an opportunity and an existential challenge to artists. And I feel like there's a kind of misplaced anxiety about exactly what that threat is. I don't know that it's necessarily a threat to creativity, more as much as it, you know, cloaks the greater danger of our kind of public mistrust in images, which in turn hides an even more dystopian reality that the world of images that we experience is dominated by a huge order of magnitude by machine images, images made by and for machines. And to use the term coined by Haroon Farouki, these are operational images, images used to survey, to monitor, to police, to navigate or control. And I would argue that artists have a vested interest in undermining and subverting these tools to interrupt these operations, such as a work like this one, which was in this exhibition, Image Interrupted. This is a work by a Ukrainian-Australian artist, Kira Brukurik. It's an installation called In the Dark, the Spiders Weave, and it restages the citizen-led tactic of handmade camouflaged camouflage, which has been used in Ukraine since the 2014 Russian invasion. And it's shown along an archive of images of Kira's family, archival video footage. So this tactic of handmade camouflage has been sort of taken up by Ukrainian defense forces over the last sort of 10 to 15 years, as the machine learning on board Russian military drones had learned to detect commercially made camouflage. So it rendered that, those camouflage nets useless. And so Ukrainian civilians would start making these camouflage nets in, town halls, in people's basements, they're sort of civic spaces. And it sort of taps into this kind of history of, textile art in Ukraine, which is a very rich tradition there. And that sort of sits beside this family archive. So there's this, on the two left screens there's images of Kira's family. And then on the right screen is footage of her social media feeds, which was sort of just showing, clip after clip of, the impact of the war in Ukraine. And I was interested in the way that this personal archive sits alongside an algorithmic archive. So these images that are sort of, continually categorized and quantified and stored by these platforms, which is, also what forensic architecture is sort of trying to unpick as well, interestingly. This next group of works is a series of photographs, cameraless photographs by an artist called Ash Garwood, who is a current UTS PhD student. And she makes these incredible, sort of nature photographs, which blend this sort of fact and fiction. So she uses this software called Cinema 4D, which is used to make kind of immersive environments in video games, essentially. And then exports this sort of 3D render, like this massive 3D render, and prints it on a sheet of acetate. So it essentially becomes a giant photographic negative, and then process it as a large format darkroom print. So this is a closer image. And you sort of see, in the actual work, you can kind of see the breakdown of the digital, from far away. Perhaps you go back, they feel quite real, but in reality, they are sort of asking you to question, the truth of the image. And I feel like it's sort of, what interested me in Garwood's works is that it's sort of creating a kind of almost a utopian vision of a kind of environment that is completely beyond our reach. There's no microplastics in these oceans. And then this is another work from this exhibition, which also has quite a utopian bent. So this is a work by Xanthi Dobby, which is called Future Sex Love Sounds. And when I approached Xanthi to make work for this show, they were really taken with the idea of asking the question, if we've reached the sort of technology future that we've been promised in, 2001: A Space Odyssey, or, a big influence on Xanthi was the Cyber Feminist Manifesto for the 21st Century by V&S Matrix, also in the Biennale this year. And Xanthi wanted to ask, well, if this is the future, then where are the flying cars and sex robots? And so this is a video. I'm going to show you a clip in a second, but basically the video, they use this kind of remix methodology of, using sort of various found materials, found sources. And they found this technology, this sort of very easily available, accessible technology to create deep fake voices for various celebrities. So if you've got enough kind of material to work from, you can make a deep fake of anyone, really. So they use figures like Morgan Freeman, Hillary Clinton, Kate Blanchett, to sort of espouse the virtues of these sex robots, which are completely customizable to any fantasy. And they've also solved all of our societal problems, which is also a huge plus. So the vision of a sort of post-labor hedonism facilitated by the offshoring of societal problems to benevolent cyborgs, I feel flips the anxiety that automation, makes human intelligence redundant. You know, when they're not taking our creative jobs, hopefully. Imagine if the machines could free us. And this is Kate Blanchett, obviously. And I'm going to attempt to show you a clip of this work. And I hope that, oh no, go back. I wonder if I just click on it. No. Nick, might need your help. Thank you. So I might just skip ahead to a kind of preferred spot. This is Morgan Freeman, obviously. I'm going to skip ahead a little bit. Thanks, guys.
I guess I should thank Eleanor and Julie for being such a hard act to follow here. So I'm an astronomer here at the University of Sydney. And before I talk about imaging, I'm going to talk about the difficulties we face. And sometimes in astronomy, we're pretty happy to get away with anything, any information rather than no information. And we'll post that as a win. So in fact, one of the first examples of this philosophy comes from Galileo, who at the time, nobody knew what a star looked like. You know, they knew there were these tiny little twinkly points in the night sky, but nobody had measured one. Nobody knew whether it was round or square. Nobody knew what the size was. And Galileo typically was the first guy to have a real crack at this as an experiment. And he wrote about this in this dialogue, which is the one that got him into trouble with the church, actually. This is a dialogue concerning the two world systems. And it's beautiful to read in this dialogue how careful he was. He went out and bought the finest thread he could. He hung a rock underneath a tree branch. And then he found a star, the bright star Vega, if you know it, in the Northern Hemisphere. And he stood behind the thread so that he could occult the star completely. And then he'd take a pace back. And then he'd see if he could still occult it. And he measured how far he had to stand behind this thread until he could no longer occult the star. And then he measured the angle and he accounted for the beam divergence in his eye very, very carefully. One of the world's most accomplished minds. And he got this number wrong by about a factor of 1,000, despite this care that he took. And the reason, of course, as we know today, is that he didn't make a measurement of the size of the star. He made a measurement of how bad the atmosphere of the Earth is at corrupting the starlight when it comes down from the heavens. So the starlight has just traveled, light years to us in pristine form. And as an astronomer, this makes me weep. In the last few femtoseconds going through the atmosphere, in fact, nanoseconds, it's all corrupted by, and what you're seeing here, basically like if you imagine looking through a bathroom window that's always changing, this frosted glass effect. We call this the seeing in astronomy. There's a word for it. And my entire career has been all about battling this phenomena and trying to basically answer Galileo's question, which in fact today still hasn't even really been adequately answered. We can't really make images of stars, which is something, if you're an astronomer and you tell people at parties you can't make a picture of a star, they're sort of, well, what do you guys do anyway? What are you good for? So one of the things that is the great privilege of the job is that the places I get to work are just staggering. This is the twin Keck telescopes riding the mists above the Pacific Ocean in Mauna Kea in Hawaii. On the left, you see the Subaru telescope, and in the distance is a distant island of Haleakala. These telescopes were brand new when I arrived as a young postdoc in Berkeley. And the first thing I wanted to do was to answer Galileo's question, to measure the size of stars. And I had the machine shop make this dustbin lid plate for me. And I persuaded, I still, to this day, I'm staggered they let me get away with this experiment. I put this over the Keck telescope primary mirror, and it stops this wonderful big piece of glass, which at the time was the shock and awe new thing in science. This is a 10-meter mirror, which is so flat and perfect. If it was the size of the Pacific Ocean, there would be no ripple larger than a foot. And you can see a guy here, and if you don't know what that is, that's a man in the middle. So it's this vast big mirror. And I'm stopping it down with my cheap plate of aluminium to about the size that an ambitious amateur could afford. But I'm stopping it down in a specific way. I'm making a real mess of it, but I'm able to, by very carefully analyzing the light that interferes between separate segments, I can turn this very large, big single mirror into what's kind of equivalent to one of these radio telescope arrays, where you link up radio telescopes on the ground. So that's sort of been where I've been going with a lot of these things. So you basically put that plate over the mirror, and you've just lost this vast amount of the starlight. With this technology, you turn the Keck telescope into what looks like a horrendous mess. What you see here is that same seeing that was in the Galileo slide before, but it's now stirring around, and what you see are interference fringes. If the telescope were perfect and it was in space, what we would see is in the upper right corner, we would see a tiny little dot. That's what opticians always want. In fact, I kind of see this as a little bit of an echo in the art world. It's like dot paintings. If you can make one perfect dot, if one star in the night sky relays on your optical system as a perfect compact dot, you're done. That's what you want. You want this perfect, clean, what we call an airy disk. So I've just gone and done the exact opposite of what everyone's telling me to do. I've made the telescope into this horrendous big pizza rather than this tiny, clean image. And using the computer processing of those interference fringes, one of the first images we recovered was this one. And I turned to the student who was working with me. I was like, there is no such thing as a spiral star. We're never going to get away with this. We've made the biggest mistake. And then we went back 2 months later, and then another few months after that. And we realized that we hadn't made a big mistake in the code. There really are spiral stars. And we had a moving target on our hands. It kept moving around like a beautiful sort of pinwheel, we call it, like pinwheel in the sky. And in fact, you can make a movie out of this object. It's a dust plume flying off an extreme hot binary star system. This is about 11 epochs, all stacked and co-registered, taken over a few years, in fact. And I'm going to try and teach everyone a little bit of astronomy here. This looks like a really complicated thing. How do you get a spiral? It's actually very, very simple. So this image on the left is stacked and co-rotated, but we start with a binary. Both stars have a strong wind, and in between the wind, there's a shock. And in the wake of that shock, dust is formed. But of course, in space, everything's it's got to be in an orbit, it's got to be moving. And so that conical shock that's where the dust is formed in a plume gets wrapped into a spiral in the same way a lawn sprinkler turns a water jet into a spiral. It's very simple physics. So we get these really clean, elegant mathematical forms out of the simplest possible dynamical system. So having got these ground-based technologies to work and being able to recover diffraction limited imagery from the ground, of course, another way to solve Galileo's conundrum with the seeing is to simply throw money at it and to put your telescope up in space. You're above the problem. There's no atmospheric corruption. The starlight is clean and pristine. if you look at the Hubble Space Telescope here, for example, this is why we want to build bigger telescopes. The airy disk, or the dot pattern that an artist would make, has a certain scale. But as we scale the mirror to a larger telescope like the Webb, the dot gets smaller. The smaller the dot here, the more resolution, the more detail we can resolve in the image. So again, you might think, now that I'm above the atmosphere and I've got these space telescopes, Peter Tuthill's out of a job. What's he going to do with his career? In actual fact, I managed to, I'll show you in a minute, there's also my technology still relevant here. But before I go there, I wanted to give everybody a little bit of knowledge they can take away, news you can use. If you ever have somebody ask you one of these beautiful images that NASA keeps putting onto the front pages of things all the time, is that a Hubble or James Webb Space Telescope image? I'll give you an insider trick to say it doesn't. The colors don't matter, the contrast doesn't matter, the number of objects doesn't matter. What you have to do is find a star and zoom in and have a really careful look. Now you count the number of spikes coming around, and then you think about the mirror that created that image. And the Hubble has got these, it's almost a perfect round image, mirror, as I was saying, the ideal we're going for, the airy disk. It's almost that, but it's got a few struts in it. The struts are there to hold the secondary mirror up. And those struts are enough to broadcast these things we call diffraction rays. So we get that kind of pattern from the Hubble. Now the Webb has got this hexagonal structure to it. And so we get these hexagonal rays. And just let me tell you for free, astronomers hate these. Everybody likes them because they look pretty. We hate them. They get in the way of stuff. We don't want them there. So we hate the fact that there's this furniture that it's required to be really mechanically. We hate the fact that there's this furniture in our telescope pupils. So it's then another piece of career irony for me that on the James Webb is flying one of my aperture masks. I actually have it meant to have it in my pocket, but I don't. It's just a little disc this large that blocks the James Webb down to form one of these non-redundant masks, just like the one that I put on the Keck telescope all those years ago. And if you look at a star field using the Webb telescope and you command the telescope to put my mask in the way, suddenly that star field turns into a beautiful little field of snowflakes. And everyone, I guess one of the points I'm trying to convey here is that sometimes doing the opposite thing to your imaging system is actually an advantage, because if you wanted to say what's going to give me the cleanest, most precise data on the nature of this scene, you would say a nice clean picture like that is much better than a messy one like this. But in actual fact, we have used now the Webb to study these spiral systems that I just showed you before. This is another slightly different one called APEP. It's nice when you discover a class of things. These are now called the pinwheels. And you can see on the far left is one of the images that's come down in the infrared. In the middle is our sort of static model of it. And that static model is the result of a dynamical process. If you just freeze it in time about now, you get almost an exact replica of the data. It's just a beautiful thing. And the lovely thing about this is that the physics is, again, so simple. It's simply a cone wrapped into a spiral, blown into a bubble, out into the void. So if we, another one of these, the last one I'll show, this one came down. In fact, this was one of the very first images released by the Webb team when they were dropping the first data sets. On the left, you'll see the data that came down from Webb. And that model you just saw before was throwing off shell after shell after shell. If you simply advance time and you say, what would it look like 160 years later, throwing off a shell every 8 years, you end up with these like set of shells all nested like Russian dolls, one inside the next. And this was essentially a prediction from the model that my student and I made that exactly explained this structure that we didn't tweak it, we didn't have to touch it. all we had to do was just say, what would it look like after 160 years of successive shells? So finally, I'll just give a little bit of a plug to my recent mission, which again leverages this weird idea. Sometimes you turn around and go backwards in order to go forwards. This is my Tolleman mission, which is meant to fly next year. It's a CubeSat, a 16U CubeSat for the people, the cognoscenti about CubeSat sort of jargon, which is about 16 liters. It flies a small space telescope, and it studies a binary star called Alpha Centauri, which is the nearest star to our sun. And the Alpha Cent A and B binary, we're interested in whether or not there might be a planet in orbit around one of these stars. And this is actually an image of Alpha Cent A and B as it would be rendered by my telescope. And you're already getting the idea. It's a horrendous mess. If I made a perfect clean telescope, this would just simply be two tiny points in a field of black. That's what orthodox optics would tell me I should build. But what I've actually done is I've taken my primary mirror and I've engraved a carving on it that makes it almost the worst possible mirror ever made by astronomers. And it turns this field of clean binary into this very messy structure. And it turns out that if you want to get the information you need, a fingerprint is way easier to register than a pinprick. And this is basically turning the two stars into these exquisitely featured fingerprints. And then I can extract the information I want from the data I get. Anyway, I think I'm past time.
Thank you. Thank you, Peter. And I'm going to invite everyone to take a risk to yourselves only, these high stools.
Yeah.
Anywhere you'd like. But if you have a mic, if you have a Madonna mic, then maybe leave the other seat for that. So we've heard a lot about how with human ingenuity and an amazingly technological and like whole teams, we can try to see things at scales unimaginable or at distances unimaginable and time gaps unimaginable. But we've also heard about the sort of the anxiety that such machine seeing is beginning to provoke, or at least the questions it asks, which is, well, if many of the images that are happening are not even passing human eyes, or if we have to deduce things, or if I have to make things like worse in order to make them better, what is the future for our our ability to see, or what forms of seeing should we embrace? And those are some of the questions that I was thinking about as you were all talking. Now, I'm sure you have loads of questions, and you must do not what I do. You must make a very brief question and put your hand up and wait for a mic. But can I just kick us all off while everyone's waiting to formulate their brief question with just a couple of sort of starters? Because I'm very interested in, just from anecdotally or in your own lifetimes, what do you think are the most extraordinary step forward? I mean, in all these histories that you're in your lifetimes, what has been the most sort of wow technological moment, and what has been the moment that's given you the most pause or cause for reflection or even anxiety? In the last, let's say over the time of your careers in the visual field.
So the advent of the space technology, that almost is a parallel with my career. I don't know if people remember this, but they launched the Hubble when I was still a student. And it was one of the first times of many that I thought I was going to be out of a job, because I thought, okay, we're now doing this from space. But then I don't know if people remember this, but when they launched it, it had an optical problem with its mirror, because they hadn't done things carefully enough. But eventually, I think in my little domain of astronomical imaging, the advent of space technologies has been a real game changer for what we do.
But hasn't put people out of work?
No, well, not within astronomy, I don't think. It's to the contrary, I think. I think it's created a lot of public interest and public excitement. I mean, the Hubble has been, of all of the telescope's ever flown. The Hubble has just paid for itself many times over in public engagement and interest. Yeah, it's been a remarkable thing. And beyond simply the narrow confines of astronomy or even science, I think it's just caused people to wonder and to think.
Indeed. Julie, is there a comparison in the microscopy field?
Well, electron microscopes have to go through a vacuum. The electrons can't fly through air. And that means that you can't use them to look at anything wet because the water just, the moisture evaporates. And I think the biggest change that's happened in my lifetime in microscopy has been that there's sort of two major developments that mean that we can now look at biological samples at really, really high resolutions. One of those is a little bit technical. It's what we call super resolution microscopy, where basically it uses a technology where there's little fluorescent things that turn on and off so that you can average exactly pinpoint where the light is coming from in the things that are turning on and off, which actually allows you to then go well below the wavelength of light and get these incredible images that show you all these detailed structures in biological samples. And that was a Nobel Prize that's been awarded in my lifetime. And the other one is totally different technology, but also solving the same issue, which is the ability to basically super quickly freeze your samples so that you take the biological structure, and when you freeze it, it doesn't become crystalline and it doesn't damage it. And so you've got the biological structures that you can look at with an electron microscope. So that's very technical, but it's been something that I've been able to witness and see change in life sciences in my life. The other part of your question was about anxiety. I used to worry a lot about the fact that it's becoming easier and easier to kind of forge images, and that it's, creating a fake image of something that can solve, that can help to try to show that there's a discovery that isn't real, used to worry me. And then I started to think about it a little bit more, and it's like, it's always been easy to forge numbers, right? We could always fake things in spreadsheets and graphs and pretend, and really it's just, it's just another way of being able to do that. And I think that it's the culture that we need to create to avoid those types of things, not preventing the technology. So I'm not that worried about the technology anymore. I just think that if something is published but never reproduced, then it will become evident that it's not real. And the same thing, it's always been easy to forge things. So I used to worry a lot about that, but I don't anymore.
Thank
you. The internet, I suppose. So I'm of that generation where, you remember the time before you had a computer at home, but and, when I first studied art history, we only looked at slides, physical slides and that kind of thing. But I suppose for, this generation of artists and curators, the ability to share images online is kind of revolutionary. Although I suppose the fears and anxieties around that are, the initial utopian promise of the internet, it being this kind of boundaryless place where you can kind of inhabit any, being and, across class and race and gender, that didn't really come to pass. And so the sort of, the internet that we've been left with is kind of a much more dystopian place. Perhaps is where I would find my anxieties most days.
Well, I'm sure there will be questions around that from. Can I ask if anyone has a question, which I'm sure you have across this room of various kinds, especially one that may be able to attract answers from more than one of our participants. Could you raise your hand, and I'm going to come round or with a mic. And remember, unlike me again, you have to speak with your mouth very close to the mic like that in order that we can hear your question.
Thank you, Mark. Jude, thank you so much, all of you, for your talks. And questions about visual literacy, which you started with, Mark, in part that you're all really good communicators because you can make us understand things that are well beyond everyone in this room will not know the particulars of each of your disciplines, put it that way. And I'm wondering how frustrating it is and potentially how lonely it is to have such enormous knowledge from a visual sense, but to work with a community around you who are really not literate in being able to understand what it is that you see. And that's as much about the sort of esoteric nature of some art history theory as it might be about astrophysics and microscopy.
Who would like to give a first great answer?
Well, I don't find it frustrating at all. In fact, I wouldn't expect that somebody who hasn't studied my discipline area for 20 years in the same way that I have would understand the technical details of the work that I do. But if I can't articulate why I'm doing it and what it's useful for and roughly how I'm doing it, then that's I actually think that's really problematic. So I think ultimately that's the thing that matters.
We're way better off than the mathematicians. I mean, we
Mhm.
deal with images, right?
Yeah.
Images are really intuitive, I find, and that no matter what the scale of the image, it tells the story itself. I bet you can just take one of your microscope images and say, well, this bit goes there, and that's attacking that cell's doing this. I think imagery is a universal language.
You touched on that anxiety question before about one of the challenges, I think, in scientific imaging, and I think this is similar in astronomy and microscopy, is that you are never actually looking at an image that's been generated with light in the same way what I see up there has been generated. And so there are artifacts, and sometimes what looks like something that you might see in the real world. So in a transmission electron microscope image, which is a really high resolution image looking at the position of atoms, what you see is little round white dots all lined up in a certain crystal structure, and you can see if they're like lined up in a cubic or a hexagonal structure, and that's important. But you look at it and you think each of those white dots is a row of atoms, but actually it's a diffraction pattern where a whole bunch of like electrons have all interacted with each other, and you're ending up with light and dark regions. And it's important not to think of it as an image and kind of sense it in the way you would naturally sense a visual image, and instead to recognize that what you're looking at is actually a scientifically generated thing and interpret it in that way.
Yeah, I mean, I don't think anyone's ever going to save the world by knowing, any particular arcane knowledge about art history, which is honestly a huge relief. But I think, I mean, I do worry, I suppose, as I touched on in my talk, that, we are less able to discern, real images from fake images. The only thing that's sort of stopping us from, really falling into the singularity, I suppose, is the fact that the fake images are so bad at the moment, like they are not that sophisticated yet. And I would want to give the general public more credit, and that they can believe their eyes as much as I can. Yeah.
Can I just prolong that just a second? You said, Julie, that it sort of takes a culture or a community to prevent some of these outrageous, like I think I know that there's a particular woman who actually goes and seeks out with her team fake medical imagery in papers and tries to, and in a way, even the most amazing benefits of that you're showing us, that is also that we can't be Leeuwenhoek anymore. We can't be the individual. It needs to take an enormous sort of structure. Astronomy is a big team game now, really, and the equipment. So I was just wondering, is that an answer, or is individual seeing more deceivable than community seeing? Is there some way that sort of collective seeing can be more rigorous than, like, as a defense against some of this fakery? Because what I heard you say there was that, it's the community that has to police itself against its own aberrations. Can we trust ourselves to do that? Or are we do we like fakes too much? Or
how are you optimistic that we can do this?
Look, I always think that there's always going to be misinformation. There's always going to be misrepresentation. There's always going to be people with less integrity. And here I'm talking about in scientific imagery and publications. And I do think there is a place for software that can detect fake images, and amazing people like, I think it's Elizabeth Birk is her name.
It's like a connoisseur in the old days. She goes and she's
she
like
can spot
Moretti
them,
with
yeah.
magnifying glass to look at.
And she puts little things on the internet where you can actually have a look and see whether you can spot the part that's been doctored. And she's incredible. And yeah, I think there is a place for all of that, but a sort of punitive approach is never really going, at the end of the day, we aren't going to be able to stop this from happening in a technical way. It's just going to get ahead of us. AI is going to be able to generate microscope images that are fake and undetectable, and really we have to kind of recognize that and then just work and I don't think we can create a society where nobody will cheat, but it's really about making sure that we've got the right kind of integrity in place to be able to operate in the world where this happens now. But they can't always pick things up, right? So I review papers, and can I tell if there's fake information in those papers? I'm not sure if that I can. I can say this seems feasible, seems like they did everything right, but it's possible that people have misrepresented results. And the pressure on, a PhD student who's got a hypothesis they're hoping to prove, and if they do prove it, they'll be able to publish a paper in a great journal, which will get them a great job, which will potentially set them up for life, compared to if their experiment doesn't work and they don't prove their hypothesis and they've got a mid-tier sort of result. It's a lot of pressure on some of these people. You can see how it happens.
So there are other questions, I think. Stick your hand up. Oh, Nick.
Thanks so much. I wanted to sort of press further on this kind of distinction between fake and real images, to ask about that point at which there's a sort of human intervention in the machine-generated images that you work with. And I wanted to ask if you have any experiences or thoughts about that moment where you perhaps exercise something that is more akin to kind of a subjective aesthetic choice or decision about an image, rather than something that's purely technical. And I guess my starting point was thinking about images of space and the way in which, we associate space with certain colors, like space is black, stars are yellow or red. And at the levels of seeing that you've been talking about, ideas of colors that appear to the human eye are sort of somewhat arbitrary. So I was wondering, do you have experience with those moments of making decisions about how things that we can't see should look, even when that's not
all the time? I mean, all of the data we recover requires a process to generate something interpretable by a human. And that process for microscopes and telescopes alike, often it's about filling in blanks, the bits you didn't measure. And there's always a process of incorporating extra. For example, Galileo there, if he'd measured the size of his star, he assumed it was round. He'd measured the diameter and he assumed an image from a diameter, right? It's a circle. He was right. He would have been right with that assumption. In fact, Newton was the first one to make an accurate forecast of the size of a star. And I don't know how he did this, but he figured out how bright the sun was compared to how bright a star was, and then how far away you'd have to walk with the sun until it was as bright as a star. And if you can imagine doing that in your mind, he did that, and he got it right to within about a factor of 40% of the correct value of the size of a star. So that was so our first forecast of the size of a star was that it will be round and it'll be this size, and it was all done without a measurement. The measurement was of Galileo's had failed. So incorporating that extra information is always something we need to do, but we need to be really upfront about what assumptions have gone into building the human interpretable thing we see, and what are the weaknesses in all of those assumptions. And there are statistical frameworks that we use to go about trying to do that impartially and carefully. I kind of think the problem is less so in the, maybe because I'm a scientist, I don't see a big problem with the curation internally in my field about people maybe making fake images, but I guess the problem I see is about the erosion of trust in all expertise in society, and the breaking of the relationship. But like, I think it was introduced that, you know, it would be hard to do my job. It would be hard to do our jobs up here because we spent ages training to do them and we did lots of math. But that idea that there are experts in the world at some things, and if you build a bridge or fly in an airplane, you need someone who really knows a lot about those things. Sometimes it seems to be more taken for granted than other times. And I think it's the gradient between the expert and the wider world. And somewhere in there, I think the problems that we're worrying about with fakes coming in and what can you believe and what can't you believe, it's curation. It's a loss of curation. And I think that's driven by the internet. Anyone can make a passable fake. Anyone can make a news site that looks like CNN. So.
Yes, a small question.
Artists have often looked at new technology in terms of how the machine generates itself. For instance, when photocopies were new in the 60s, a number of artists worked with photocopies self-generating themselves. And in a sense, I mean, your explanation of the different ways in which the Hubble images is a form of self-generation, isn't it?
There certainly are assumptions that go into those images that are made, but I mean, there isn't well, I'm an astronomer. We believe there's an objective truth out there, and that there is something we're looking at that has certain morphology or form. And we trust our instruments, not perfectly, but to try and render that in ways we understand. The more self-generated imagery is something I think is coming more from the, I guess we're seeing a lot of that in generative AI, where you can start with a field of noise and you can generate pictures of donkeys or dragons. We try to avoid that in the cleaner sciences, where we're trying to render a scene with as much fidelity as we can.
What we do in microscopy sometimes is a simulated image. So we assume that we're trying to solve whether a material has a particular structure, protein or something. And what you do is you assume that it has that structure, and then you model what it would do if an electron beam went through it, and this is what the image will look like. And then you compare that to the image that came out of your microscope, and then you say, oh, okay, well, they look similar or they don't look similar. And there we're generating a heap of simulated, self-generated sort of images in order to work out a fixed truth, which is the structure of the molecule itself.
Can I ask a question? I was really, is that okay, Mark? Yeah. Peter, I was so taken with the idea that you make the image messy in order to create the information that isn't otherwise there in a cleaner image. And I wonder, Julie, if there's a similar sort of methodology in microscopy. You know, are you ever kind of trying to get kind of more complex or sort of more, more noise in the image?
There's something very similar in the technology, in that if you put a beam through a crystalline sample you'll just see like a nice round beam of light. But if you block out the beam of light that goes directly through, and you look only at the light that gets diffracted or gets like pushed off to the sides, then you can interpret a heap of extra information about the arrangement of all of the atoms by looking at how it's diffracting the light or the electrons in different directions. So really what you're doing is, it's not actually that you're adding complexity in that case, you're blocking out the main information in order to be able to detect the more subtle stuff. Yeah.
Art historian with their details, where you have to look at the something over there, thing that seems to be the subject.
Yeah, that's right.
Each one is talking about very like different place. You are out there, you are very little, you are the mundane, like the line we are looking, and it's all about technology. And so for me, the question is where the emotions, which is from human beings, can connect the technology out there in little normal. How can we navigate with emotions and how it is validated or expressed?
That's a great question. I mean, I suppose, that, artists are tasked with that, very thing of finding the human in everything. And I hope that in the examples that I showed, there was a sort of feeling that there was, the presence of real people in there. But yeah, I don't, I mean, I suppose the actual researchers are the sort of the people, this is their life's work, their life's passion, and we wouldn't have any of this amazing research without those real emotions. Yeah.
I'm not sure about emotions, but creativity is very important as a scientist to be able to construct an experiment that's going to solve a problem, and you very often have to find a new and creative way of approaching it in order to be able to get new information. And with a microscopy experiment, probably a bit unlike astronomy where you are observing something that's fixed, you're actually deciding what to put under the microscope. And sometimes you're actually designing the sample where you've manipulated it in some way or you've built it in some way in order to discover something about the thing that you're putting under the microscope. And that is a very creative process. And in fact, some of my colleagues who are less creative, don't do as well in the discipline area, even though they are brilliant mathematicians or that's not the right word, but technically very capable. So creativity is I think, under-recognized skill for scientists, I guess is all I'm trying to say.
Yeah, very much so. I know I find it quite an emotional thing to be a scientist. And part of the difficulty of the job is conveying that, because when you get a new result or something that you think is awesome, cool, and you realize you're so far up this tree that you've climbed that it is hard to convey why it is actually so cool to your mum and dad or to your kids or something. Yeah, it's a bit of a personal emotion then, because you can't really go and tell anyone about it unless they're on your corridor. So that's where you need to be a good communicator and try your best, I guess.
And it's an absolute roller coaster of a job. Like, you do experiments that work and that's amazing feeling. You do things and you do a lot of stuff that fails and that sucks. And you, constantly applying, putting in papers that are accepted or rejected. And it's like, it's an absolute roller coaster of a job.
Thank you very much for your fascinating talks. My question is kind of similar to Nick's. Rather than the subjective aesthetic judgment, I was talking, because you're all speaking about scale and, very minute in your case, and then, beyond imagination in astronomy. And I was just wondering about, you know, the representation of things, you know, like when you say, like when you see pictures on social media of the NASA Chandra X-ray and or interstellar columns or this star that is dying or being born, or in your case, when you see these very minute things, which are just a representation of a electron beam or light hitting an electron, you know, and then Benjamin talks about when he looks at Carl Blossfield's pictures and he says like worlds like hiss up like geysers, you know, different forms of seeing. This is where my question is about that assumption of what things should look like and what you are actually seeing. You're seeing things beyond the imagination and you're reducing them to something that can be recognized. In that reduction, what are we losing is, you know, like, you know, you were saying there's an objective truth out there. Who is kind of the determining kind of evaluator or arbiter of that? Is kind of the big question.
A couple of questions, but both very interesting.
Would anyone like to try and tackle it? Either the scale question or the index question in some ways?
I can start with the
you go.
scale question. So just to tell you, poor Galileo, he was trying to witness the size of a soccer ball in Singapore. That's the angular size of the nearest star. He was looking, you know, he was looking at a very large, bright star in the night sky. So he's trying to see with his naked eye the diameter of a soccer ball in Singapore. That's why he couldn't do it. One of the things that always staggers me in science is just the crazy success of mathematics and the crazy success of our instruments. And that although it sounds like some of the measurements we make might be subjective, at some level, we have processes to verify, to cross-validate, to authenticate other people's work. The images we do produce out of these machines, there may be some fuzziness at some boundaries, and you may be able to interrogate or question some aspects of it. But by and large, we can show each other's work is right. And that even though it sounds staggeringly difficult, it's an incredible lever you've got when you've got these vast telescopes and these precise instruments. It's kind of like you're this cyber suit. You can do things that Superman couldn't do. It's really amazing.
And anyone else want to comment? I mean, your other question is about sort of where, if we're going to evoke Benjamin and him putting on the problems of like, so then what is the, like in a court of law in the future, what is going to stand up? Like what is photographic, or, you know, the image as index of some kind of truth or witness to some kind of real happening in our new 21st century existence? Are we going to simply have to jettison certain assumptions that we've made about like what images can do or can't do, or what particularly the photographic, talk of photography falls apart, like is in the end, is what you're all doing so amazingly going to sort of undermine something about what we thought photographs were doing or certain kinds of image capture were doing?
Is it just representation? Is it a map or a drawing rather than is it an illustration rather than the true? Yeah. That's such an interesting question. I mean, I would refer back to the work of forensic architecture, because I think that's a really interesting case in, you know, an example of photography, you know, the example of photography used as proof. And it is, you know, photography in its, you know, in its essence is was designed for in some ways and perfected by, you know, the criminal justice system, by the way that, you know, things can be proven through physical evidence. Exactly. And, you know, a lot of the current work, or, you know, maybe 10 or 15 years ago, the work of forensic architecture was looking at sort of, you know, the single grain of a sort of silver gelatin photograph would be the sort of exact, you know, position, you know, GPS position of what they were trying to find. And so it's sort of hidden in the grain of the photograph in a way. And, you know, now we sort of look at pixels. But no, I think photography will continue to have this incredibly important discursive sort of purpose for, various settings outside, the visual arts. But I think it's probably more of an existential question for the hard sciences, because that is the sort of their, the evidence of their research and their work. Yeah.
So part of your question there, you were asking, is there, by rendering something into a form that we can understand as an image, are we losing information, and do we even know what that information is that we're losing? And I think in some cases we don't. And a microscope image isn't just like an image with light and dark either. Usually we're also measuring the X-rays that come off at each point in that image. And then we can use those X-rays to work out what elements are, which atoms are present, which types of atoms they are. So you've got like a depth of information across your image that you're also collecting. It might be diffraction information that tells you the orientation of the crystals, or, as I say, X-rays to tell you what atoms are there. And there is an increasing trend now towards actually collecting that whole set of data from these images, and you may only be looking for, I don't know, the arrangement of the atoms on that surface, but you've also got all the diffraction information just there stored in the data set, and you can come back to it later on. And, it increasingly happens that you refer back to old data sets to answer new questions, because you actually realize that you can interrogate that data in a different way. So that's happening more and more, where we're digging up old microscopy data sets and then applying new computational approaches that we didn't have before to solve new problems. So there's information in there that we don't even know is there.
The modeling is not like extreme stellography or whatever. That modeling is the kind of seeing.
Well, I mean, you demonstrated sort of your mathematical seeing and how your mathematical prediction of what something, a model which was created by maths, right? What you showed us was mathematics vision, if you like.
Yeah, in my world, a model and an image are very intertwined, and you just have to be very upfront about which parts of it, what assumptions go into that. Yeah.
Okay, maybe we have time for one last question. I'm conscious that everyone, nice, last.
Thank you. Thanks. Hi. Yeah, professionally, I'm an IT engineer, but I'm deeply fascinated about the space exploration and what lies beyond our planets. So yeah, the question is, we had Hubble Space Telescope, which was deployed for the deep space, and it really did so much. It found so many objects in this space, and we deployed Webb Space Telescope later. But I believe it was deployed to find out if there is any other intelligence exist in the other planets or any other objects in this space. But is this the James Webb Space Telescope? Is this actually working as expected, or is it deployed to find the more deep space, or actually to find out some other intelligence in the objects? So I think, yeah, this question is to Peter. Yeah, thank you.
So the Hubble Space Telescope is called the Hubble because it was designed to, in fact, measure a constant of the universe called the Hubble constant, which was the rate of expansion of the universe. It's sort of the parameter that astronomers use to measure how far we are sitting in the middle of a kind of a fossil explosion, an explosion that happened at the beginning of time. And it's been 14 or 13 billion years ago, and we can still see that explosion streaming away from us in every direction. So that rate at which that goes that's why the Hubble is called the Hubble. And in fact, it's funny because quite recently, people wrote a list of the most important things the Hubble telescope had done, And the measurement of the Hubble constant was one of them, but it didn't rate the important list. All of the things that it did were not the things that were in the proposal to get the money from Congress in the first place. So that's one of the great things about building versatile instruments like Webb and Hubble. Both of them will probably, the things that we don't yet know that they'll do will probably be far more interesting than the things we designed them to do. The main difference between the Hubble and the Webb is that the Webb is dedicated to the infrared. So it observes radiation that's all of it invisible to our eyes. So every time you see a Webb image, you are not seeing anything that can be rendered in any realistic way for your eyes. Your eyes cannot see this radiation. So it's always false color. And there are many reasons why the infrared is very important to astronomers. And in fact, it's important to astronomers for the same reason it's important to the military, because often infrared imaging is used on desert battlefields where there's lots of dust. The US military used them to great effect in the Gulf Wars. They could see right through all of the dust from the explosions. So we use it in astronomy for the same reason. We can see through lots of obscuration, and we can witness the skeletons of things that otherwise would be behind opaque walls of intervening material. You alluded to the idea of extraterrestrial life. I would love to be saying that I've got a proposal on Webb. I've got proposals on Webb, but not to find extraterrestrial life. We have to find whether there's even a place. Yeah, we have baby steps. We've got to find whether there's planets there could be life. We're not even sure there are. We're now sure there are many, many planets, and that's a new thing. Yeah.
I can't believe there is nothing like this slide. The idea is so fascinating. The one small tiny object, the planet, the existence.
Yeah, most stars have a planet. So there's lots and lots of planets out there.
So we've gone rather big at the end there. And maybe the fact that we can't really see the things except unaided should remind us of the complicated relationship between humans and machines, that in fact, without a good framework of working together with our machines and our human communities, we are going to be casting around or infernally foiled one way or another. I just want to, I realize that we're going towards the end. Lots of people have lots of places to go. So, but before we all do go, I'd just like to say a massive thank you to our panelists. So so much. Thank you all for coming. Thank you again to Nick and to all the Chau Chat Wing team who made both the exhibitions and the programs available to everyone. If you're interested in all of the Chau Chat Wing programming, it's on the Chau Chat Wing website. And if you're interested in Power Institute programming, you can catch us at powerinstitute.org.au, where other programs related to our interest in sort of new ways of seeing can be found. So thank you all very much. And thanks again to everyone.